Hi everyone. So in this video we are going to see how to use the restoring method of division. The most important fact about this method is that uh, it works only if your operands are in signed magnitude representation. So, as you know, there are different representations possible for binary numbers, and the signed magnitude representation is quite basic. So, here, according to this representation, you have to store the sign of the given operand separately in a flip flop, and the rest of the part of the operand, that is the magnitude, is stored in some fixed sized register. So if you have this kind of binary numbers, then only restoring method of division can work. Okay, so let us take one example to understand how this method actually operates. So let's say we want to divide plus 136 by minus 9. So these are the our operands. Now, as we want to use signed magnitude representation, let us first decide how many bits are needed to represent the magnitude part. For the sign bit, obviously, one bit is needed for storing each sign of each of the given operands. So let us represent minus 9 first. So as the sign is negative here, you have to keep the sign bit as 1, and this will be stored in a flip flop. Let us call it BS. The magnitude part, that is the actual value, will be stored in a register called B. Now, what should be the size of the register? That will decide shortly. But let us first see how many bits are actually needed to represent 9 in binary. So 9 in binary is 1001. Similarly, to represent this value, the first operand, the dividend in binary, we need a total of 8 bits. So binary of 136 is 1000 1000. And as the number is positive, the sign bit will be a 0. So let us store this value as AS or QS. So here we have a total of 8 bits, and here for the divisor we have a total of 4 bits. So one basic rule that the restoring method of division follows is that your dividend should have 2n bits and your divisor should have n bits. So here that criteria is already followed. So let us understand how to store this 2n sized dividend in registers. So if we take 4-bit registers, then we need two registers here. So the first part of the dividend, this is the least significant part, low part, that will be stored in a register. Let us call it Q. And the second part, the high part of the dividend, will be stored in register A. So we need a total of three registers to store the two given operands. Two registers for storing the dividend and one register for storing the divisor. Now, what will be the sign of this dividend? The every register, this is our assumption here. Every register will have an associated sign flip flop. So A register has its sign flip flop as AS. Similarly, QS is the sign flip flop associated with the register Q. Similarly, for register B, the associated sign flip flop is BS. So here, whether you consider AS or QS, the value will remain a 0. That indicates the positive sign of the dividend. So this is the initial configuration. Now, before we start the actual division, we have to check one possible error, and that is known as divide overflow. So the basic meaning of the divide overflow error is that when you try to divide the given operand by the divisor, at that time, after performing the division in the quotient, if you get n plus 1 bits, that indicates the divide overflow. As you have seen here, the operands are stored in n bit registers. Though we have used multiple registers to store the given values, the size of each register is fixed, and that is n bits. So in the quotient, if you get n plus 1 bits, then there won't be enough space to store that n plus 1 bits in any register, because you have kept the fixed sized registers and the size of every register is n bits. So because of that issue, the restoring method of division cannot perform the actual division, it cannot produce the correct answer, and it will fail. So if a divide overflow is possible to occur for the given operands, then you cannot proceed with this method of division. Restoring method of division will simply not work if a divide overflow is present. Another possible error is division by zero. So, as we know, division by zero is undefined for computers, and that's why before we perform the actual steps of the division, we have to take care of these two errors. So, here, according to the logic of the restoring method, one condition is required to be checked before we can proceed with the actual steps of the algorithm, and that logic, that condition checking, actually takes care of both the probable errors, division by zero as well as divide overflow. So let us do one thing. For the given operands, let us first check whether both these conditions are satisfied. Our divisor should not be zero, and there should not be any possibility of having a divide overflow after the operation. So let us see what condition is to be checked that will take care of both these probable issues. So here, if A is greater than or equal to B, that means a divide overflow will generate. So what is A and B in our example? We have taken our dividend as 136, dividend as 136, and the high part of our dividend is A. So in our case, A is 1000 and B is the divisor, that is 9. So 1001. Note that we don't have to do anything with the sign bits. They are stored separately in flip-flops, and they will be used only in the end to determine the sign of the final answer. So right now, whatever logic is required to be used for computation, that will be performed only on the magnitude parts. So this is A and this is B. Now, if A is greater than or equal to B, then we have to stop. In that case, this method will not work. So what we need to do here, if we want to compare the magnitudes of A and B, subtraction is one of the basic options. So let us find B bar plus 1 first. Basically, we want to do A minus B. If A minus B is 0, that means A and B are equal. Even if it is not 0, we can comment on the magnitudes of A and B. So we'll see how that is done. But first, let us find the 2's complement of the second operand, the subtrahend, because we want to perform A minus B. So B bar plus 1 will be 0 1 1 1. 2's complement of this. So we have to add this 2's complement of the subtrahend to A to find A minus B. So this will be all four ones. So here no AND carry is generated. The result of the subtraction is of n bits when we take two n bit operands. So this additional bit, let us call it E, the AND carry bit. So E is clearly 0 for this example. No fifth bit is generated, no additional bit is generated, so E is set to 0. So here, based on the value of E, we can actually comment on the magnitude of A and B. So if E is 0, that means A is less than B. In that case, we can proceed with the actual steps of the restoring method. So here what we have done, we have actually performed this operation. A minus B is implemented as A plus B bar plus 1. Now the result of this subtraction is currently stored in E and A. If no additional bit is generated and plus 1th bit is generated, E is simply set to 0, but the main result of the subtraction is available in A. Now A is actually the high part of your dividend. You have updated it because of this subtraction. So if you want to proceed with the actual algorithm, first you have to restore the original value of A. So, is due to subtraction, A is updated. If you perform addition, the effect of the subtraction can be nullified. So, here to restore A, what operation you need to perform? Addition of A and B.